Here's a set of data which represents a random variable, but this random variable is a little bit different. It's not discrete. So this is an example of a continuous random variable. If you haven't taken the time to read the setup of the question here, read the setup of the question, pause the video, read the setup of the question, and then start playing the video again. So the random variable represents the player's batting average. So that's a Major League Baseball player's batting average. We are describing the shape as a normally shaped distribution with a mean of 0.261 and a standard deviation of 0.034. So what's important to recognize here is we can't make a list of all of the possible batting averages and their probabilities. With a discrete distribution, we could list all of the outcomes and all of their probabilities. We can't do that here. So, for instance, let's say someone has a batting average of 0.289. Well, the truth is it really 0.289 or did we round that off? Was it really 0.2887? Or was it actually 0.28873 repeating? I mean, there's no way to list all of the possibilities and all of their probabilities, and there's no need to. So this distribution is not discrete. So instead, we call this one continuous. And the reason we call it continuous is because the shape of this distribution can be modeled by using a curve that is continuous. It doesn't have any breaks or gaps or jumps in it anywhere. We'll show you that in a second when I show you how I want you to demonstrate your work. So knowing that the shape is normal, knowing our center is at a mean of 0.261, and having the standard deviation as a measure of our spread, so that standard deviation is 0.034, we can use z-scores in order to find the corresponding probabilities or even percentages of outcomes. So our first question is, what's the likelihood that we randomly select a Major League Baseball player and their batting average is 0.3, is 300 or higher? So the probability of a batting average that's greater than 0.300. For the record, this is a decent batting average for a Major League Baseball player. So how likely is that? And the way we can calculate that is by determining what percentage of outcomes in this distribution will be at 0.300 or higher. So the way to do this is to take that 0.300 and first convert it into a z-score. So to build that z-score, we take the observation, we're going to subtract the mean, and then we're going to divide by our measure of spread. We're going to divide by the standard deviation. What the z-score accomplishes, it tells us how many standard deviations above or below the mean this observation happens to be. So you'll have to put that in your calculator. There's 0.300 minus 0.261. And then we'll divide that by the standard deviation of 0.034. And we'll get our z-score. It's important to round your z-scores to the hundredths place, to 2 decimal places, because that's the level of accuracy that's available to us when we're using the table to find these percentages or these probabilities. So this z-score is 1.15. And to represent your work, you should really draw a picture, because that picture communicates the model that you are using. So here is our continuous model, our normally shaped model or distribution. So because we've converted to z-scores, z-scores always have the same mean, 0, and they always have the same standard deviation. That standard deviation is 1. So when you draw this picture, you can draw this picture literally for each question when you're using the normal distribution. This is the model we're using. But then to find your probability, the boundary that we're working with is 1.15. So you should include that z-score as the boundary for what you're trying to calculate, and we're interested in values that are at or above that 1.15. So this is where we would shade within our distribution, and to find that likelihood, we need to look up the 1.15 in our table. So remember, in the z-score table, the first side of the z-score table has our negative z-scores. So we want to work with the second side, the positive z-scores, and we want 1.15. So here's 1.1. So to get the 0.15, we have to go 1, 2, 3, 4, 5. We have to go over 6 columns. So there's the 0.05 to get the hundredths place. So our likelihood is 0.8749, but that is the likelihood at 1.15 or below. So what you just found was this. That's what you found. That's 0.8749. So you're really interested in this likelihood here. So you need to take that answer and subtract it from 1. So 1 minus the 0.8749, that will give us what we're looking for. So that's a likelihood of about 12.5%, 0.1251, and we're done. So the next question is a little bit more straightforward, the likelihood of a batting average below 0.190. So just like the previous question, we'll convert this into a z-score. So there's the observation that we care about, minus our same mean divided by that same standard deviation. So this time, instead of showing it on the screen, I'll just go ahead and do it quickly here. So 0.190 minus the 0.261 divided by our standard deviation. That comes with a z-score of negative 2.09. So using our model has a normal shape. We're working with z-scores, so our z-scores will have a mean of 0, and we'll have a standard deviation of 1. And we're interested in values that are below or have z-scores that are even smaller than negative 2.09. So here's our boundary. And because we're working with a below question, this is the area that we would shade in the distribution. That's what we care about. So we can look that up in our table. Again, this will be on the first side of the table because I'm looking at negative 2.09. So here is the negative 2.0. And to get the hundredths place, we have to go all the way to this end. So this is, there we can see it now, this is an unlikely outcome. This is 0.0183. So literally you're done once you label it. There you go. So the last type of problem that we could do is where we're trying to find the likelihood of a particular range of batting averages. So we're interested in the likelihood of a batting average, or in this case, the percentage of Major League Baseball players that will have a batting average between 0.25 and 0.275. So we need to convert both of those boundaries into z-scores. Again, we're using the same formula, the same mean, the same standard deviation. And this question, it's really important to label carefully, because when you label your graph carefully, it will give you an important hint, and that's the order in which you want to do your subtraction. So this is another question that's going to involve some subtraction. So knowing the order in which to subtract is important. So this first z-score, if we round it, is negative 0.32. The second z-score should be positive. Let's see. 0.275 minus 0.261 divided by the 0.034. That gives us a z-score of 0.41. So if we draw the picture that we care about, again, here is our shape. Our center is at 0. Our standard deviation is still 1, but I'm interested in the percentage of observations between negative 0.32, so maybe we'll put that boundary here, and positive 0.41. And I'm interested in the percentage of observations between those. So you're going to have to look both of these up in the z-score table. So the negative 0.32 I can see right here. Here's the negative 0.3, and we'll have to go over to the 0.02 column to get our value. That's 0.3745. So that gives me this percentage. So if I look up 0.41 in the table, what it does is it gives me the percentage of observations at 0.41 and below. So I'm going to look up 0.41 in the table. Here we are. Here's 0.4, here's 0.40, here's 0.41. That's 0.6591. But I'm not interested in either one of those. I'm actually interested in the difference between those. I want this percentage here. So that's actually the difference. That this is the value that I want here. This is actually the difference between the 0.6591 and the 0.3745. So we'll calculate that and we'll be done. 0.6591 minus the 0.3745, that looks like 0.2846. So literally the percentage of Major League Baseball players that are going to have a batting average between the 0.250 and the 0.275, it's about 28.5%. There we go. Hope this was helpful.